Moving on, let's now examine how pressure and flow rate influence fluid power. It should be well within your capacity to understand that power is the time rate expenditure or production of energy. Power is energy over time. Depending upon the system of units employed, customarily power is expressed in units of foot-pounds force per second, units of horsepower, or watts, where 1 watt is 1 joule per second. Energy, in contrast, is commonly expressed as force times distance. Common units of energy are foot-pounds force and joules, where 1 joule is 1 newton of force expressed at a distance of 1 meter. There are several perspectives one can use when calculating power, one being the output mechanical power of the system, the other being the input fluid power. On a simplistic level, calculating output mechanical power of a system requires knowledge of the force exerted, the distance traveled, and the time required to do so. Given a 2,400 pound weight lifted 12 inches in 5 seconds, we can calculate that the mechanical power exerted is approximately 480 foot-pounds force per second. If we needed to express this in units of horsepower, it would be roughly equivalent to 0.872 horsepower, or in units of watts, approximately 651.1 watts. If one, however, was only capable of observing the fluid properties, namely pressure and flow rate, one would have to go through a tedious series of calculations to arrive at this value. Allow me to demonstrate. Assuming we're using a cylinder with a 2-inch cap diameter, a 1/2-inch rod diameter, with a travel length of 12 inches that lifts on extension, we would expect to observe the following functional areas and volumes. The cap end functional area is approximately 3.14 square inches. The volume of the cap at full extension is approximately 37.7 cubic inches. Assuming this cylinder lifted a 2,400 pound object on extension using the cap end functional area, we can use Pascal's law to calculate that this cylinder would necessitate an input pressure of at least 763.9 psi. Given the cap end volume of approximately 37.7 cubic inches must be filled in 5 seconds to fully extend the load, we can use our knowledge of flow rate and actuator speed to calculate this cylinder would necessitate a flow rate of at least 7.54 cubic inches per second, or approximately 1.96 gallons per minute. Now, if one was only capable of observing pressure and flow rate, rather than the observed force, distance, and time, one would have to perform the above calculations in reverse to see how this system would respond. This is an option. However, a shortcut exists which I'll demonstrate now. If power is to be expressed in units of horsepower, flow expressed in units of gallons per minute, and pressure expressed in units of psi, one can directly calculate hydraulic power as pressure times flow rate divided by the constant 1714. I'll explain the origin of the constant in a moment. Substituting in the observed pressure and flow rate, we arrive at 0.872 horsepower. Exactly as previously, and without the messy necessity of calculating functional area, volume, or actuation time. What is this magic, you say? I can assure you that pulling units of horsepower from PSI and GPM stew isn't magic, but rather mathemagic. The mysterious constant 1714 is a result of a string of unit conversion that takes some time to wade through to understand its origin. Pressure is expressed in units of PSI, or more understandably, pounds force per square inch. Flow rate is expressed in gallons per minute, more simply, 1 gallon over 1 minute. Given a gallon is 231 cubic inches and 1 minute is 60 seconds, units of square inches cancel out, and we're left with 231 over 60 pounds force inches per second. You can see where this is going, right? Given 1 foot is 12 inches, we can express this as 231 over 60 times 12 foot-pounds force per second, which, if you recall, is a base unit of power. Given we need to express this power value in horsepower, along comes another unit conversion. Given 1 horsepower is 550 foot-pounds force per second, we can express this as 231 over 60 times 12 times 550. What is 231 over 60 times 12 times 550? To be relatively precise, it's 0.000583. However, it's customarily expressed as 1 over 1714. Ta-da! pressure in units of psi times flow rate in units of gallons per minute divided by 1714 yields power in units of horsepower. Do not think I am asking you to memorize this unit conversion mess. All you need to be able to do is put pressure and flow rate and power in the proper units and use this formula. Allow me to demonstrate the utility of this hydraulic power shortcut one more time in the manner it would be traditionally employed rather than the back calculation as I did previously. First, let's do it the hard way and pretend no shortcut exists. Given a cylinder with an 1.5 inch cap diameter, a 1/2 inch rod diameter, and a travel length of 16 inches that lifts on extension, we would expect to observe the following functional areas and volumes. The area of the cap is approximately 1.767 square inches, and the volume of the cap end at full extension is approximately 28.3 cubic inches. In the act of extension, let's say we're observing a pressure of approximately 600 psi and a flow rate of 1.3 gallons per minute. Again, we are going to do it the hard way first, no shortcut, but a rather good old-fashioned mathematical ground pound. Let's start with a brief unit conversion. 16 inches is approximately 1.33 feet, and a flow rate of 1.3 gallons per minute is 300.3 cubic inches per minute, or approximately 5.005 cubic inches per second. Given the cap end functional area lifts on extension, we can use Pascal's law to calculate that this cylinder would exert an extension force of approximately 1,060.3 pound force. Given a flow rate of 1.3 gallons per minute, or roughly 5.005 cubic inches per second, we can use our knowledge of flow rate and actuator speed to calculate that this cylinder would fully extend in roughly 5.65 seconds. Now all we have to do is put it together to arrive at a power figure. A force of 1,060.3 pounds force was exerted at a distance of 16 inches, or approximately 1.33 feet, over a time span of 5.65 seconds. This results in a power expression of 250.25 foot-pounds force per second. If we wanted to express this in units of horsepower, we'd have to do a unit conversion to show this is roughly equal to 0.455 horsepower. Look at all the work it took to get here. Now, let's try the shortcut. Given an observed pressure of 600 psi and a flow rate of 1.3 gallons per minute, we substitute these values into our shortcut power formula and find this system is exerting 0.455 horsepower. Ta-da! Look at all the steps and time we saved. Using the shortcut, one does not need to know actuator dimensions, functional area, volume, Pascal's law, nor actuation time. One simply looks at observed pressure and flow rate and walks away with a fluid power figure. Now realize this simple example is assuming there is 100% efficiency, an obvious fallacy. Given an actuator is a fluid power to mechanical power converter, one can assume only a portion of fluid power input actually gets converted into usable mechanical power, the rest being lost to inefficiencies like leaks, friction, heat, or noise. Assuming we really are exerting 1,060.3 pounds force, a distance of 16 inches, or approximately 1.33 feet, over approximately 5.65 seconds, we are definitely observing 250.25 foot-pounds force per second, or approximately 0.455 horsepower output. However, let's say we're observing an input pressure of 650 psi and a flow rate of 1.4 gallons per minute. Our shortcut fluid power calculation yields an input of approximately 0.53 horsepower. Given the actuator is applied 0.53 horsepower and exerts only 0.455 horsepower, we can therefore say that this actuator is approximately 85.7% efficient. Before closing this lecture, I should briefly mention constant horsepower applications, in which flow and pressure are regulated, such as the title implies, power is constant. Given a constant power output, and either a pressure or flow figure, you should be capable of solving for the unknown flow or pressure figure. Allow me to demonstrate. Given a constant 2 horsepower system producing 10 gallons per minute of flow, determine the pressure. An algebraic rearrangement of our hydraulic power formula suggests that pressure equals 1714 times hydraulic power divided by flow rate. Substituting in the given values yields a pressure of approximately 342.8 psi. Similarly, if pressure increased to 2000 psi, we could rearrange our hydraulic power formula to solve for flow. Substituting in the given values, we find flow has decreased to roughly 1.7 gallons per minute. You note when flow output is plotted as a function of pressure requirement for a constant horsepower application, it forms a rather uniquely identifiable curve. At any point on this curve, the product of pressure and flow yields a constant power output, in this case our given value of 2 horsepower. As one would expect, if power is constant, flow rate is high when pressure requirement is relatively low. Similarly, flow rate is low when pressure requirement is high. It makes sense. And if you understand how pressure, flow, and hydraulic power are related, it can't not make sense. For those interested in testing their understanding of the above concepts, I leave you with the following challenge problems. I'll try to put the answers in the information section associated with this video. Challenge 1. Given a conductor with a 3/4 inch internal diameter carrying 4 gallons per minute, determine the fluid velocity in units of feet per second. Challenge 2. Given a hydraulic system supplying a pressure of 900 psi and a flow rate of 2.6 gallons per minute to an actuator, determine the hydraulic power input to the actuator in units of horsepower. Given the actuator lifts a 2,500 pound weight 1 foot over the span of 5 seconds, determine the mechanical power output in units of horsepower and the efficiency of this actuator. Challenge 3. Finally, given a constant horsepower application with regulated 3.5 horsepower output, determine the flow at 200 psi and again at 1500 psi. Alright, I believe I discussed what I intended to do regarding fluid velocity and fluid power calculations. Unit conversions, math, and constant derivations aside, you should realize there is a relationship between fluid velocity, flow rate, and cross-sectional area, and fluid power, pressure, and flow rate. In conclusion, this lecture took a brief introductory look at fluid velocity and fluid power calculations. Additionally, we defined laminar and turbulent flow conditions. Finally, we briefly discussed constant horsepower applications. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.